Hi, my name is Wang Xinghan, and I am honored to have the opportunity to present my paper titled Neural Koopman Pooling, Control-Inspired Temporal Dynamics Encoding for Skeleton-Based Action Recognition. As shown in the left figure, most existing works use a CNN or GCN backbone to extract spatial temporal features from the action sequence, and then use temporal average pooling to aggregate the information. However, action sequence has complex underlying dynamics. Average pooling contains only first-order information and abandons high-order information. In this work, we focus on the true latent dynamics of the sequence and use class-wise linear dynamics to represent class-specific dynamics evolution patterns, which can be used for classification. We also proposed an eigenvalue normalization technique to ensure stable and non-decaying dynamics. Suppose X is the feature sequence extracted by the feature extraction backbone. Existing pooling methods include vanilla average pooling, which average the features along the temporal dimension, and covariance pooling, which uses the covariance matrix as the pooled features, and bilinear pooling, which captures the interaction between temporal features by calculating weighted inner product. However, these methods still overlook the latent dynamics of the sequence. Instead, our proposed Koopman pooling linearized the sequence dynamics and then use the linear transition matrix K as the signature of the whole sequence, which contains rich high-order information. To be specific, unlearnable matrices Ki is set to represent the linear dynamics of each class. To conduct sequence classification, we have to compare the dynamics of the given sample, which is governed by K, and the class-specific linear dynamics, which is governed by Ki. To this end, we propose to use L2 distance of one-step linear evolution on the feature X by K and Ki. In this way, the class activation score can be derived as the linear fitting error. The resulting overall architecture is shown in the figure below. The proposed model consists of three parts, namely the mapping to the Koopman space, the class-wise Koopman evolution by Ki, and dynamics matching by the linear fitting error, which yields the score. The spectrum and the eigenvalues of Koopman matrix K are very important for system dynamics evolution. In this part, we address the critical importance of system stability for recognition tasks. An eigenvalue with a modulus smaller than 1 will cause the mode to eventually decay to 0 over time, while an eigenvalue with a modulus greater than 1 will cause the system to be unstable and divergent. The figure shows the visualization of the original trajectories and their one-step linear evolution. We can see that the learned system is a decaying system, which causes class mismatch during classification. To this end, we proposed an eigenvalue normalization method, which pushed the eigenvalues to be near the unique circle. This results in a stable and non-decaying system. We also look into the task of one-shot action recognition. Under this setting, only one sample from each novel class is provided as the exemplar, which makes it important to fully exploit the information of the exemplar. As there's only one sample, the model cannot learn the dynamics matrix from data like the manner before, so we leverage dynamics mode decomposition to calculate the matrix directly from the given sequence. Then classification can be achieved by matching with the calculated class-wise matrix. We conduct experiments on three benchmark datasets, namely NTU RGB60 and 120, and NWCLA. The overall results is presented in the table. As we can see, the proposed Koopman pooling improved the accuracy of CT-RGCN by a non-trivial margin, especially on the large-scale dataset NTU 120. The table on the left presents the classification accuracy on each modality. We can observe that the performance gain is very consistent across the modalities and datasets. The upper right table shows the results under one-shot setting. Notice that the performance gain is very significant. We also conduct ablation studies to prove that Koopman pooling is effective across various spatial temporal backbone, which is shown in the lower right table. This figure presents the visualizations of trajectories after the eigenvalue normalization. Compared with the figure shown before, we can see that the decaying issues is greatly alleviated. The trajectories of one-step linear evolution by the dynamic matrix of ground truth class manifest similar patterns with the original sequence. Also, the trajectories of the same class exhibit highly similar patterns. This is the end of my presentation. Thanks for listening.